In this video, we'll be showing you PASCO's solution to investigating the properties that determine the resistance of particular conductors. To start off, we have the PASCO resistance apparatus. Contained here are all our wire samples that we'll be using for this experiment. Various different conductors, same lengths, a couple different diameters. And then this is powered by the 850 interface. So to start off, we will plug the connections of the signal generator into the appropriate slots on the resistance apparatus for power. And once we make all these connections here, then we have a voltage sensor that will go into the analog A input on the 850. And then we'll connect the voltage sensor leads to the sliding probes on the resistance apparatus. Now, it's important before you start that you have read the procedure and gathered all your materials ahead of time. Now, once you've done that, go ahead and open the pre-configured Capstone file. It comes with the lab. And when you do this, make sure, once again, review the theory and setup. I'm going to jump right into the procedure here just for this video. So to start off, we're going to double check and make sure all of our connections are secure and made. And then we will go into the data page and we'll start collecting some data after we load our first wire sample in. So the procedure says start with copper. It really doesn't matter, but I'm going to follow the instructions and insert the copper. Now, if you, it's recommended that you measure the diameter with a good pair of micrometers if you have access to one. If you don't, we have supplied the diameters on the setup page of the Capstone file. So when setting this up, I just like to insert it through one end. Make sure to loosen and make sure that the sliding probes are parked up on these plastic tabs here so that you can slide the wire through without them getting caught. It's very important that your wire is very straight also, because any bends in the wire will create points of altered resistivity compared to a straight wire. And a bent wire is more difficult to read the actual length compared to a straight. Now, you may be noticing there are two sets of white lines right down here. These are actually to help you align the wire on both ends, so you have two white lines here as well. So I'm just going to get it roughly in place and tighten it down, and then do the same thing on the other side. Just move it over and just give it a nice finger tight. Don't over tighten these, otherwise they will break. So now we can take the reference probe and set it to the 0 mark on the apparatus. Now we can take the sliding probe and we'll move this to the 5 centimeter mark. Now that we have this physically set up, we need to go back and confirm some settings here. So because this is copper, we want to make sure that we have the voltage gain on the sensor set to 1,000. And the same thing goes for aluminum. So we got to change this to 1,000 and click OK. Once we've done that, we can start collecting data. I'm just going to input, actually, here, we'll start right now. The way this is set up on this screen, this voltage, it's what's being read by the voltmeter here. And then the current is measured by the signal generator's output. And then using those two measurements, we use a calculator equation here to apply Ohm's law, which is seen right here, to give us the resistance value that's measured. each incremental distance that we're going to be measuring. So let's go ahead and open the signal generator as well. Make sure the DC voltage is set to 2, and I like to have it set to auto, so it'll turn on and off when I start and stop recording. So I'll go ahead and close that, and we can hit record now. And we'll hit stop. And we'll start populating the table with data here. So this one's 1.1. And then we'll move the slider to the 10 centimeter position. And take a new measurement. Just let it settle for a few seconds. All right, and record that value for R, which is 2.15 mega ohms. Then move the slider to 15. Right, and hit record again. Let it settle for a few seconds. Okay. 3.21. And then we'll slide this to 20. Record. And we'll hit stop again and record that value. 6. And then we'll move the slider to the last position, which is 24. And hit record. All right. And we'll record that value. So now we have a complete data set for copper. So what we need to do now is go into the data summary and need to delete all these extraneous runs, except the last one. The last one will have all 5 data points included in the table. Once we delete these, let's rename this appropriately since this is for copper. Or you can put CU, whatever is convenient. Okay. So now we've collected our first set of data for one wire sample. For all the other wire samples, aluminum, nichrome, steel, and the one of the brass, the procedure follows the exact same as we did here. So now that we've done this, we've collected our data, we can go over to the graph now and get an idea of the relationship we'll see between the length and resistance. So let's go copper. So as we see, as length increases, we're seeing an increase in resistance, which is in line with what we see in theory here. Increase in length increases the resistance, just due to that equation. And so now we got the slope of this line right here. This slope is what will help us determine the resistivity of that material. And so to do that, we go to this next page, which once again, we input values that we already know. Whoops. Either by measurement directly or from reference. And then we'll enter the slope. That was 0.211. And so when we enter these two values, there's a calculator equation that will calculate the resistivity for this particular case. Then we get about 1.69, which is pretty close to measured for copper. This could be due to multiple things, corrosion of the samples or things of that nature. And then we repeat the same process for the other samples and answer your conclusion questions. So that's the first part. That's looking at the length dependence. The next part involves looking at the area of different wires. And so we have 4 brass wires of different thicknesses, rather diameters. And we're going to be keeping the length of measurement the same, but just varying the actual wires themselves. Now we've got to remove the copper and actually make sure you park the reference probes first before loosening the screws. Okay. And notice you have a nice storage tray here for your wire samples during experiment. Otherwise, I recommend storing them inside the tube in which they came. So now for the brass samples, let's populate the data table with our sample sizes. I'm just going to use the ones here from setup. 5182, there we go. Oops. 1.27. Just double check. Yes. Okay. And the process is going to be very similar as before. Be sure to carefully slip the, I'm doing the smallest wire first. Be very careful with this one because it is the most likely to bend and maintain deformity. So, once you've got it in position, tighten the screws down. And go to the other side. Go. Move the reference probe to 0. Then move the sliding probe to 24. And now because we have the brass samples in, we need to go back to our data summary and we need to change the gain to 100x right now. Right. And then we can hit record here and let it settle for a few seconds. 85.15. Go 16. Okay. And then we repeat this same process for the other samples. Get me still not following what I'm saying. We'll do the next sample. Once again, move the reference probe back to 0. Move the sliding probe to 24. Hit record. I'll say 34.25. Swap this out, make sure to park your sliding probes first and then loosen. You'll notice when you do it correctly, it doesn't pinch or bind when you loosen the screws while the probes are still in contact. That's why it is important. And the third one. I'm wearing gloves also, as you may be wondering, so I don't transfer any of my oils onto the sample pieces here, which can affect the conductivity on the surface. Right. Do the same thing. Reference probe to 0. Sliding probe to 24. Hit record. All right, record that value. Once again, park your probes, loosen your screws. And load the last sample. Same thing. Tighten those. Move the reference probe to 0. Sliding probe to 24. Making sure you're on the center of the hash marks. And last time, hit record. Let it settle for a few seconds. All right, 1284. So now we have this data set. We can go over to area dependence. Actually, I need to do the same thing that we did here. Need to delete that run. Delete that run. Oops. Oops. Just going to rename this. Let's see. Oh, there it is. There it is. So here is the graph of all of our data points. If we, for example, do a quick calc, and let's say we take the inverse of this. And if we take the inverse, we should see that our data is very linear in this case. And in fact, it is. So we can see from this graph, because I took this quick calc and inverted this axis so that now the graph is linear. What that means is the relationship between the area and the resistance is inverse. And then from here, you can go on and answer all your analysis questions. Hope you found this useful. If you have any additional questions, please reach out to teacher support.